Hello and welcome to the YouTube channel D Creations Resources. We are discussing several aspects from science, and especially we have been discussing a lot about spectroscopy, different electromagnetic radiations. So today let us talk about a filter used in X-ray diffraction. Now as you know, X-rays are an electromagnetic radiation with a wavelength regime of few angstrom. Now, in an X-ray diffractometer, a filter plays a crucial role in producing a more monochromatic or single wavelength X-ray beam. And this monochromatic X-ray beam is essential for obtaining clear and interpretable diffraction patterns. So, the common source of X-rays is X-ray tubes, and generally these produce beams not just of one wavelength, but they generate a spectrum of X-rays consisting of two main kinds. One is the continuous spectrum, that is Bremsstrahlung radiation, and another is characteristic radiation. So continuous spectrum is a broad range of X-ray wavelengths produced when electrons decelerate upon hitting the target material. The target material could be copper, molybdenum, etc. in the X-ray tube, while characteristic X-rays are sharp and intense peaks. They show sharp and intense peaks at specific wavelengths which are characteristic of the target material. So they arise from the ejection of inner shell electrons in the target atoms and the subsequent filling of these vacancies by outer shell electrons, releasing energy in the form of X-ray photons of specific energies. Now, when you say specific energies, it also means specific wavelengths. So typically, the most prominent characteristic lines are K alpha and K beta lines. And now if you consider Bragg's law, n lambda is equal to 2d sine theta, where n is the integer, the order of lambda is the wavelength of X-rays, d is the spacing between the crystal lattice planes, and theta is the angle of incidence of the X-ray beam on the crystal plane. Now, for a given set of crystal planes, the diffraction angle at which constructive interference and thus a diffraction peak occurs is directly dependent on the wavelength of the X-rays. So, if there is a polychromatic X-ray beam, then each wavelength in the beam will diffract at slightly different angles and for the same set of crystal planes. So, there would be an XRD pattern in which there are overlaps of the diffraction peaks that can happen. So then it's very difficult to accurately determine the D spacings, and so then you know that we determine the D spacings to understand more about the crystal structure of the material, whichever is being analyzed. So then it's very complex and challenging for interpretation. So instead, what we do, or the solution comes in terms of a filter. Now, an X-ray filter is a thin sheet of a specific material placed in the path of the X-ray beam emitted from the tube. What is the role of the filter? The role of the filter is to selectively absorb certain wavelengths from the spectrum and ideally leave behind a beam that is predominantly of a single wavelength. So basically, it should filter out the unwanted part, and only a monochromatic beam should be the result which is obtained after using a filter. What is the working of a filter? So filters work on the principle of absorption edge. Now every element has specific energies, and of course every time I say specific energies, I also intend to say that specific corresponding wavelengths at which its X-ray absorption coefficient increases sharply. Now these are the absorption edges. I repeat, every element has specific energies at which its X-ray absorption coefficient increases sharply. These are the absorption edges related to the binding energies of the electrons in its different shells like K, L, M, etc. So a K-edge filter is commonly used in X-ray diffraction to isolate the strong K-alpha characteristic radiation of the target material. Now the material of the filter is chosen such that K absorption edge lies between the K alpha and K beta wavelengths of the target material. Let's take an example. Copper is one of the most commonly used target material, and the filter used here has atomic number just one less than copper. So copper is 29 and nickel is 28, and nickel is the filter used. Why is it used? Because if you look at the copper K alpha wavelengths, copper K alpha is around 1.542 angstrom, while copper K beta is around 1.3922 angstrom. Now, you have to look at the K absorption edge of nickel, which is around at 1.488 angstrom. So what is going to happen? Wavelengths shorter than the nickel K edge, like copper K beta, are going to be strongly absorbed by the nickel filter, while wavelengths longer than the nickel K edge, like copper K alpha, are going to be transmitted more readily, although some absorption can still occur. So if you carefully select the thickness of the nickel filter, the intensity of the unwanted copper K beta radiation can be significantly reduced, while still allowing a significant portion of the desired copper K alpha radiation to pass through. So the necessity of a filter is for production of a monochromatic X-ray beam, and due to its use, now the diffraction pattern is simplified and you can accurately determine the d-spacing, and hence the subsequent crystal structure can be accurately determined. Thank you.